Welcome to our chapter, Renewable Energy Potentials. In this video we give an overview of spatial and temporal renewable energy potentials such as biomass, geothermal, solar, wind energy and hydropower. Firstly, we define the term of renewable energy potentials such as economic, ecologic and social acceptance potential. Secondly, we show the spatial distribution of the economic renewable energy potentials in the EMENA region and on a global scale. Finally, we compare time series showing the temporal availability of the economic renewable energy potentials. The characteristic of the temporal availability of renewable energies is essential building systemic energy scenarios, which could lead to a balanced energy mix.
In the following we define different renewable energy potentials. These are the theoretical, technical, economic, ecological, and social acceptance potential. The collective intersection of the mentioned potentials is defined as the expected potential. The theoretical potential of a renewable energy describes the energy supply that can theoretically be used physically within a given region and a period of time. The technical potential is the share of the theoretical potential that can be used, considering technical restrictions. The economic potential is the share of the technical potential which regards total cost of energy conversion from a renewable energy source. The total cost must be in the same range as cost of comparable systems. The ecological potential is the share of the technical potential that does not lead to any additional permanent impairment of the habitat. This is considered in terms of diversity and interactions between creatures and their environment. The social acceptance potential is the share of the technical potential that can be used, considering attitudes as well as social and political restrictions. The expected potential is defined as the intersection of the economic, the ecological, and the social acceptance potentials. In this video we focus on the economic potential.
In this evaluation we show the economic electricity potential in EMENA for biomass, geothermal, solar, wind energy and hydropower. The yield is measured in gigawatt-hours per square kilometer and year. Biomass and geothermal energy have a yield with up to 1 gigawatt-hour per square kilometer and year. Wind onshore and wind offshore, as well as hydropower follow with 5 to 50 or 0 to 50 gigawatt-hours per square kilometer and year. The largest yield has solar energy with a yield between 10 to 250 gigawatt-hours per square kilometer and year. This equates to a 250x of the biomass, or geothermal, and a 5 to 50x of the yield of wind energy or hydropower. Nevertheless, solar power has different characteristics compared to other renewable energies, thus it is seen as one component for the energy mix among many others. Only a systemic spatial and temporal analysis, including for example grid and storage technologies, can reveal the optimal shares of each renewable energy for the energy system and a balanced energy mix. The economic electrical potential of renewable energies in the EMENA region is calculated with over 600,000 terawatt-hours per year. This could cover the global electricity demand, with around 25,000 terawatt-hours in the year 2022, by multiple times, all renewable. Hereby the major potential have the solar power technologies photovoltaics and concentrating solar power. In the year 2010, the electricity demand in the EMENA region is approximately 6,000 terawatt-hours, whereby Europe consumes about 2/3 of the total demand in EMENA. Until the year 2050, scenarios expect that due to population development, the rise of gross domestic product, electrification of the heat and mobility sector, as well as water desalination, the electricity demand in the EMENA region doubles to around 12,000 terawatt-hours per year. Hereby, Europe and the MENA region share this demand each with around 50%.
In the following we go on global scale and consider the economic potential, including technological cost assumptions, restrictions of land use such as protected or populated areas as well as terrain slopes or coastal distance. We focus on wind on and offshore, photovoltaics and concentrating solar power due to their high potential yield per square kilometer and year. The economic potential is shown as temporal function of capacity availability in full load hours per year. 1 year with 8,760 hours and a spatial resolution of around 50 by 50 kilometers are the references. This gives an impression of the spatial distribution of renewable energies and their potential capacity utilization. Here we show full load hours of wind on and offshore. The results are calculated with a minimum resource boundary condition of an annual mean wind speed of 4 meters per second at a height of 50 meters. Areas such as tropical forest has no wind onshore potential. However, high full load hours of over 5,000 hours per year can be achieved in hotspot areas such as Alaska, Patagonia, North Sea, Horn of Africa, Japan and Tasmania, and thus on every continent. Regarding photovoltaics, the spatial availability and economic potential is given almost everywhere. Full load hours of photovoltaics can be up to 2,150. In regions lower 30° northern and southern latitude, the full load hours can reduce drastically under 1,500. In tropical areas, full load hours are also under 1,500 due to rainfall and aerosols. Concentrating solar power plants have a more limited spatial availability due to their resource with direct normal irradiation. A minimum threshold of 1,800 kilowatt-hours per square meter and year is assumed. The resulting economic potential is concentrated on each continent. However, more than 2,500 full load hours of the solar field can be achieved in desert regions such as Mojave, Atacama, Sahara, Namib, Rub al Khali, Gobi, and in Australia.
The use of the economic potential of renewable energies requires a temporal view on their availability to cover the demand in time. Here we show in a so-called isopleth diagram an hourly resolution over 1 year referred to Coordinated Universal Time, UTC, starting at 1st of January. Provided data are from the year 2006. In our example, the electrical load of Germany is shown. High load accrues during the day and in winter, while load is reduced on weekends and in summer. Having a look on the availability of photovoltaics, we show the availability in the western part of North Africa and the availability in Germany. In North Africa, the daily availability during the year from 9 a.m. to 5 p.m. is almost constant with constant high daily availability. This constant day-night cycle behavior can support the use of storage. In Germany, the availability is given in summer from around 6 a.m. to 8 p.m. and reduces in winter to the time span between 8 a.m. to 4 p.m. Due to clouding, the availability of photovoltaics in Germany is often scattered. However, time spans in summer show a high availability of photovoltaics. The reason of the different solar availability is the rotation of the Earth's inclined axis, which contributes to the formation of the seasons. The closer we get to the zone of the tropics, the more even the day-night cycle is throughout the year. Regarding transmission and distribution of electricity, it is not practicable to transmit the same generation profile of photovoltaics from North Africa to Germany when in Germany at around the same time photovoltaics provide locally already electricity. The idea of a transmission of energy from North Africa to Germany is to supplement the local generation by using dispatchable solar power including storage to enable high full load hours of the power plant and transmission infrastructure almost constant during the year. The availability of wind offshore and wind onshore in Germany is shown in the present isopleth diagrams. The availability is weekly and almost seasonal constant. Wind offshore and wind onshore have a higher availability in winter than in summer. Wind offshore can reach its maximum availability almost constant during weekly time spans. Wind onshore also reaches its maximum availability, however, only in sporadic time spans. Regarding transmission and distribution of electricity, wind onshore can be installed close to centers of demand, avoiding high transmission line and grid expansion.
In this video, we define renewable energy potentials and show that the economic renewable energy potential in Yamena can cover the world electricity demand multiple times. Hereby, solar power technologies can contribute with the highest yield per square kilometer and the highest economic renewable energy potential. Thus, dispatchable solar power, its transmission from desert regions, can contribute value for the energy system as one major supplemental component. Biomass, geothermal, wind and hydropower can also contribute to a balanced energy mix regarding their temporal availability. This leads to the conclusion that only systemic energy scenarios can reveal the optimal shares of each renewable energy for the energy system and a balanced energy mix. If you cannot see the full picture, a wisdom says, if you doubt, zoom out. Feel free to follow and contact us via social media or email.